Hi everybody, this is Mr. Zarzak, and in this video I am going to discuss what happens when we charge up some parallel plates. So let's get to it. All right. These are some parallel plates that have been charged up, one positive, one negative, opposites attract. Okay, so what we've got here is a bunch of charges hanging out on the surface of the insides of these plates. All right, the way that we get this to happen is what we do is we take each of our plates and, well, at least one way we can do it is we connect a voltage source across the plates like that. All right, now the whole voltage across part, that's really more of a circuits thing. Okay, so we'll get into that more later. All right, well, we just want to focus on what's going on in between the plates right now. Okay, so if we can put some positive charge on one and some negative charge on the other, we get this. Okay, we get a uniform electric field. So voltage and field are connected together. If we look at the AP equation sheet, kind of the two biggies, all right, that we have been working with that relate together, voltage and electric field. So there's this. So the change in voltage is equal to the negative integral of E dr. All right, and we also have this other equation. So EX is equal to negative dV dx. All right, now what the one on the bottom says is that the derivative of the voltage with respect to position will get you the electric field in a certain dimension. Okay, that's what the e to the x is. All right, it's really, the top one is really, if you integrate the electric field with respect to position, you get back to voltage. These two equations, okay, they really do say the same thing. Just one is the integral form and one is the derivative form. Now, the negative sign that's there, okay, if we go over to our plates, our electric field in this case points to the right. All right, well, if you want to increase in voltage, if we want to give the positive charge more energy, we have to move against the direction of the electric field. So like the higher voltage would be to the left in this case, the lower voltage would be to the right, okay? Well, anyways, so what can we do with this? All right, well, if I take this e to the x equation, okay, I'm going to work with that one since we haven't done as much with that. If I just move the dx over, so e to the x dx is equal to the negative dv. All right, now where the negative sign is, which side doesn't really matter, so I'm going to shift it over here, all right, because really we're trying to get back to that integral equation. All right, then if I take and I integrate, okay, both sides, all right, well, the integral of dv, that's just going to be our change in voltage, like literally, oops, delta V. Okay, other side, okay, if our electric field happens to be constant, which for parallel plates, look, it's constant electric field, that's exactly what we want. Okay, well then EX is just some constant, so really I'm just taking, if I pull that constant, I'm taking the integral of dx, okay? And much like if I take the integral of dv, I get the change in the voltage, okay? If I do that, I get the change in position. Okay, just like that. All right, so now when we say change in position, all right, well, if I go back to my plates here, what is that? Delta x. Okay, that's really just how far we go from one side of our plates to the other. Okay, now we just call that d for distance. Okay, so when we manufacture, when we build the capacitor, okay, one of the parameters that we can control is how far apart these plates are from one another. Okay, and that has an effect on the behavior. It's kind of like if you've ever, walked across a carpeted room with your socks, okay, and then gotten shocked when you touched a doorknob or a light switch. Okay, it's when that d gets small, all right, that we get the discharge. It's not when we're farther away. So it's the field is dependent upon that distance of separation. It's one of the things that shows up. Okay, anyway, so going back over here, all right, for the purpose of our parallel plates, okay, we just kind of write it like that, that negative E times D is equal to the change in voltage. Okay, and then one more step too. All right, when we're talking about capacitors, very often we're going to work with like absolute value. All right, what I mean by that is the voltage across these two plates, okay, is not dependent upon which way I connect the voltage source. Like my capacitors can be wired into a circuit in either way. So like right now, okay, going back to this, we'd put it in like that. Our voltage is this way. But if we instead flipped around, okay, our terminals, okay, yeah, where the positive charges and where the negatives are would switch, but the voltage across the capacitor, the number of volts would remain the same, like 5 volts from one plate to the other. Okay, so that's kind of why, and also helps get us to this next thing, which is going to be the capacitance. All right, so that's where we're going. All right, so just for this, just think like the size of the electric field times the separation of the plates tells me the difference in the volts between one plate and the other. Okay, all right, next we're going to look at the electric field between the plates. Now, in general terms, to get the electric field, we apply Gauss's law. Okay, so let's go back and do that. So we got E dA, that's a terrible way. I'm trying to, is equal to the Q enclosed over epsilon naught. Okay, and from Gauss's law, we know it's almost always that Q enclosed that we have to pay attention to. Okay, so then if we go back here and say we look at one of the plates, okay, let's positive one. All right, we have a surface charge density. Okay, so those little positive charges are going to distribute themselves uniformly along that inner surface of the plate, so we get a sigma. Okay, so this is area charge density. Okay, that's equal to the charge enclosed over the area, okay, that we're interested in. And we can also write that as the total charge over the total area. Okay, so the density, the density of the charge density doesn't change whether or not we're talking about the whole plate or just part of it. Okay. Well, anyway, so I'm going to take and say sigma times A is equal to Q. Okay, and I'm going to use that in Gauss's law. So I get this E dA is equal to sigma A over epsilon naught. Okay, and that dA here is this is the shape. All right, now for the parallel plates, remember we don't really care what the shape is. Okay, any old A will do because, well, that A is just going to cancel right out. Or we've seen this idea before. And we're just left with the electric field. Oops, let's stick with black. The electric field, okay, above one of these plates is just sigma over epsilon naught. Okay, so then what can I do with that? Well, I now have two relationships that have E in it. Okay, so I'm going to put those two things together. All right, so I'm going to take this sigma over epsilon naught. Okay, we'll make it in red to make it shiny and show up. Okay, and I'm going to take this, I'm going to plug this in to this ED is equal to delta V. So multiply by D, and we get delta V. Okay, awesome. So what? Well, the new kid on the block here, okay, the new concept is capacitance. Okay, so capacitance is defined as the charge divided by the change in voltage. Okay, we introduced that a little bit ago. All right, well, I have this relationship for delta V, so I'm going to put these things together. So Q over delta V, where I have delta V, I have this sigma over alpha, okay, times D. All right, now that epsilon naught is down in the denominator, so let's get that up in the numerator. Okay, so now we're just kind of doing algebra. All right, so then we have C is equal to Q epsilon over sigma times D. Okay, this contains charge and it contains charge density. When we build a capacitor, we don't have control over the charge or the charge density. We're going to get that out of there. Okay, so the way that we do it is we go right back to here. Okay, that sigma is equal to Q over A, specifically. All right, for my actual physical capacitor of a fixed area, there's some amount of charge that we can put on it. Okay, and so that's exactly what I'm going to do here is C is equal to Q epsilon over Q over A times D. All right, and when I do this, Q's cancel. Okay, so I'd have epsilon over D over A. So then just to clean that up a little bit, no mixed fractions. All right, we get this. The capacitance of parallel plate capacitor is equal to the area of one of the plates times epsilon over the distance of separation between the plates. All right, that is your basic parallel plate capacitor equation. And if we look at it, what does it depend upon? It depends upon the size of the plates. That's the A. It depends upon epsilon, which is just that permittivity constant, okay, and it depends upon how far apart the plates are from one another. That's it. Okay, and those are all things that we can control if we were going to build this. We can build bigger plates. We can put them closer together or farther apart. And by doing that, we control the capacity, how much charge, where is that little thing for capacity? How much charge is going to fit on these plates for a given voltage that is applied to them, but we do it without controlling the charge or the voltage. That's kind of cool. All right, this one is so common, all right, that this actually shows up on the AP equation sheet. So let's take a look at that real quick. Okay, so then here it is. This is the parallel plate capacitor equation, but then there's an extra letter in front, that K. That is not Coulomb's constant. No. That's the dielectric constant. Okay, so that's that little multiplier. A dielectric is an insulator. Okay, so something like plastic, like a nylon or a glass, or it could be like paper or wood or rubber, or like I said, any dielectric is really just an insulator. Okay, so they give it a different name because we're now talking about it in a different capacity. Okay, so let's talk a little bit about dielectrics. Okay, so to complete the equation, put that little K in there. Okay, and it's supposed to be in a different font too. All right. Actually, I wanted to point out one other thing on the sheet too, real fast. So if we go down a little bit, okay, this is something else. This one's actually new this year on the AP equation sheet. The way that we could calculate the dielectric constant is by measuring the relative permittivity of the electric field in the material. So you measure the strength of the field through the insulator, and you divide it by that permittivity in a vacuum, okay, which means that you're taking one measurement that has one quantity. So if we looked up the units for epsilon naught, it's gross, but the units for epsilon is the same as epsilon naught. So this K is a unitless coefficient. It's a multiplier. So if I put some plastic or some other insulator in between my parallel plate capacitor, I get a boost into how much charge I can fit on there, or how much capacitance I have for a given voltage. All right, how does that work? Okay, like this. All right, so this is supposed to be a representation of a dielectric. So we take a piece of plastic or glass or something and we put it inside. All right, and what happens to that insulator? It's going to polarize near the surfaces. Okay, like when we have an insulator, okay, all that means is that the charges, the little electrons, have limited freedom of mobility and they are less delocalized, all right, than they are in a conductor. So like in a conductor, electrons belong to everything, okay, and they can push around wherever we want with inside the conductor. With insulators, not so much. However, all right, we can polarize. So see, like we haven't added or taken any charges from this piece of plastic. Okay, we just induced like a line of negative and a line of positive over here. Okay, and well, one thing that we know about electric field lines is they're supposed to start on positives and then on negatives. See, so some of those electric field lines terminate at the insulator. Not all of them. You see some of these go across. Okay, so what's really happening here is by adding in this insulator or this dielectric, we reduce the electric field between the plates. Now, why does that matter? All right, well, we have this relationship. So we have this delta V is equal to negative E times D. And again, we're interested in magnitudes here. Okay, if we take and we reduce, so a dielectric reduces the E field, okay, well, then the result of that is for the same distance of separation, keep the plates just as far apart. Well, then what must happen is that the voltage across our plates also reduces. Okay, well, what does that mean? Well, capacitance is just defined as the charge with respect to the change in voltage. So if all of a sudden our voltage gets smaller, well, then our capacitance is increased. All right, now what that physically means for us, okay, because very often when we connect these things, what we will do is we will hook them up to like a fixed voltage source, okay? So then if we maintain the voltage, or just another way to think about this, all right, well, the dielectric increases our capacitance. So then if we take and we hold that constant, okay, well then, sorry, that's an arrow. This is supposed to be. Well, then the only thing that can happen is that means for the given capacitor, that means we can cram more charges on those plates, okay, before we have so many to where we get a discharge, to where we get a spark across the two plates, okay? So the dielectric increases the capacitance by decreasing the electric field, okay? So that's kind of the basics. All right, some other stuff that I want to consider here. Okay, that's just a note for me, so don't worry about that. Okay, so let's say I take a conductor and I put it in an electric field. Okay, well, we know, all right, from before that we don't have any electric field in a conductor in the static case. All right, so no field inside the conductor. So what? Well, those little lines, that represents the electric field. Okay, so the electric field before the conductor, okay, the lines are spaced evenly far apart. I see just as many number of lines on the right side as the left side. Okay, so point is that if I have evenly spaced electric field lines, I have a constant electric field. All right, when I get into the conductor, the electric field drops off to zero. When it comes back out, the electric field, okay, returns. Okay, so like the lines end and then begin again. All right, what we would really be doing is we'd be polarizing the conductor. Okay, well, we've talked about that before. I want to focus more on the shape of what we would see if we were to say graph, okay, the electric field. Okay, so I'm going from left to right. So like, if I'm going this way, okay, what would I see? Well, when I'm in here, okay, I have some constant electric field. When I'm in here, I have no electric field. And when I'm over here, I have that same constant electric field again. It's like we punched a hole in the electric field. So then what would that look like? Let's see here. I tried to get fancy with this. There we go. It would look like that. Okay, a constant value, then nothing, and then a constant value again. Okay, those are just those little dashed lines are asymptotes. Okay, well, now what about the voltage? Okay, well, I can see it right down over here. I mean, I gave myself like some talking points here. All right, the voltage would increase from 5, so go, so look at the little tick mark. So we get like 5, 6, 7, 8. Okay, it would hit the conductor. All right, no change in voltage inside the conductor. All right, when I come back out, okay, you can see the tick line. So let me count. So this is 5, and then 6, 7, 8. Okay, when I come back out, I'm still at 8. So no change. Okay, so there's 8, 9, and then this would be like my 10 line here. Okay, so anyways, so going back to this, all right, the voltage is going against the slope. So like to increase the voltage, okay, like I'm going this way, I'm going uphill, all right? So if I were going to look at that like on a graph, okay, I would see the voltage increase, but then when it hit the conductor, there would be no change inside the conductor because there is no electric field. And I mean, think about it, right? For a constant electric field, okay, that gives it times the distance, that gives us the delta V. Well, inside the conductor, there's no electric field, so there can't be any change in voltage. Okay, so all that means is that the voltage is going to build up, okay, to some value. Again, we're going from left to right here. Okay, so the voltage builds up. Okay, then when we hit the conductor here, okay, it remains constant. It plateaus. We get no delta V because there's no field in there. But then when we leave again, okay, the voltage would continue to rise. And the size of the electric field here versus the size of the electric field here is no different. I mean, I can see it right here on my graph. Okay, and that just tells me that the slope of my voltage, okay, is going to be constant both before and after. It's going to be the same value because the slope of the voltage with respect to location, that's the electric field. That's that e to the x is equal to v dx. Kind of cool, huh? All right. Anyway, so what about this? All right, it's a little different scenario. I have these plates. Okay, so if I could do 2 plates, why can't I do more? The answer is you can. Okay, so I've got these plates energized to different voltages. I got a 10 volt and a 5 volt and a 5 volt and a 0 volt. Okay, so then the first question is what does the electric field look like between these 2 things? All right, so from here to here, my voltage goes down. What does that mean for the field? Which way does the field point? Well, to increase in voltage, I would need to go against the field. So to increase in voltage, I would need to go against the electric field, which means that the electric field is pointing in the opposite direction of my voltage rise. So for this case, the electric field is just going to point to the right. Okay. Now, if I look at the next 2 plates, okay, I have a 5 volt and a 5 volt. There's no change in voltage here. Okay, there's some distance of separation, but again, we're playing around with this little idea of, I erased it. So delta V is equal to E times D. There's no change in voltage here, which means that there's no field in between these 2 plates. See, so nothing to draw. All right, last 2 plates, 5 volt, 0 volt. Okay, I drop down in voltage. So kind of like with the 10 to the 5, okay, I get a 5 volt drop that tells me the direction that the field is pointing. It's pointing this way. Okay, and because the difference in voltage is the same, the strength or the size of the electric field is the same too. All right, now what the heck would that mean? Okay, well, remember the electric field is the force on some small positive test charge, right? So if I took a little positive charge, I released it here, it would get accelerated, it would get pushed by the field, so it would speed up, speed up, speed up, speed up, speed up until it entered this region, in which case there'd be no field. So what it would do is it would maintain constant velocity, right? The object in motion stays in motion in a straight line at a constant speed until it emerges in this region. Once it gets in here, it's back in an electric field, so now it's going to accelerate again. Okay, so from here to here, speed up, maintain constant speed, speed up again. All right, what would all this look like graphically? So same 2 questions. Okay, what does the electric field look like first? Okay, well, first region, here. Okay, we have some constant value for the electric field. In here, no electric field. In here, some constant value for the electric field. So again, we've got similar to what we had before. Ooh, now it's pink. Great, we'll stick with pink. Okay, so we get electric field, okay, in this first region here, nothing in here, and then in the same constant value over here. All right, what about the voltage? Okay, well, we go from 10 down to 5, okay, and then we stay at 5 for a while, so we decrease in voltage, we maintain a voltage, and then we go from 5 down to 0, okay, so the shape of this, now we did pink, we got to stick pink, okay, it looks like that. All right, and again, we have a constant value for the electric field, so the point is that the magnitude of the slope here for the voltage is a constant value too, so we get a decrease that's a straight line as opposed to a curve. All right, pretty neat. Okay, now let's put some numbers to this. All right, this last part about this is, so we got these parallel plate capacitors. Notice I got the positive charge on this side. I got the negative charge over here this time. Okay, and down at the bottom, the difference in voltage between the two plates is 4 volts. So we go from 2 volts on the right all the way down to negative 2 volts on the left. So we got a delta V of 4. All right, now up here, okay, the gap. Okay, the total gap right here, okay, it's just these together. Now, why do I have this separated out? Well, you'll see here in a minute. First, we're going to analyze this with just the 2 plates, and then I want to take and I want to put a conductor in between. So we'll do that in a second. Okay, that's why I got the regions. All right, but we can see that if we put these things together, okay, well, then the total separation, the total D, is just going to be 5 millimeters, which in meters is 0.005 meters. Okay, all right, well, from that, I can figure out the electric field. Okay, so I'm still playing around with this idea that this delta V is equal to the negative ED. Okay, I'm talking magnitudes here. Okay, so just how much voltage is across these plates. We know what it is. It's just a 4-volt change to go from one plate to the other. Okay, well, so what? Well, if I know that, then I can take, and if I take the voltage divided by the separation of the plates, I can tell how strong the electric field is. I know which way it's pointing. It's pointing to the left. Okay, my change in voltage is 4 volts. Okay, and my distance of separation, that's that 0.005 meters. Okay, so that's going to tell me my electric field strength. Okay, so 4 divided by 0.005. All right, so 40 divided by 0.05. So what is that? That's 800. Okay, now notice the units. Okay, that's volts per meter. Okay, now I know we've been working with newtons per coulomb. Okay, but remember a volt is a joule per coulomb. Okay, and also remember that a joule is a newton per meter. Okay, and so we wind up with this. there's your newtons per coulomb. Okay, so volt per meter and newtons per coulomb are equivalent units. Okay, in this capacity, because we're talking about applying a voltage to some plate separated at some distance, volts per meter is probably more appropriate. Okay, I have a constant electric field. If I was going to graph that simple, okay, looks like that. Oops, it looks like this. Constant electric field. Okay, what's that mean? Well, to go up in voltage, okay, that just means I'm going this way. Okay, now I start down at -2 and I end at +2. So I think it probably conceptually is an easier picture. Let me extend this out to the end of the graph. Okay, I think it's probably easier to draw it like this. Okay, so we go up from, below 0. Okay, we end up above 0. Okay, so we're going from -2 up to 2. So something like that, right? Like the slope of the VD graph is constant because the electric field is constant. Okay, all right. So then now what happens if I take and I insert, okay, this conductor? I put another piece of metal on the inside. Like we threw an insulator and we threw a dielectric. So why can't we do a conductor? And the answer is we can. Okay, now we know that we don't get electric field inside the conductor. Okay, so the shape, so what this is going to look like is going to look a little different now. Okay, it's going to look more like that. All right, now what's not going to change is the voltage between these two plates, okay, is still 4 volts, all right? Like that's controlled externally. We control that by connecting it to a voltage source, like a battery. We plug it into the wall, okay, we get some change in voltage of 4 volts, okay? So has anything changed? Yes, something has changed, okay? So now look here, all right? So we got 2 volts here, we got -2 volts on one side, +2 volts on the other side. There can't be any change inside this. There's no delta V in here, okay? So what does that mean? It means that to go from here to here, we're going up 2 volts. So see, like right here for this particular case, we're at 0 volts. See, and there's no delta V inside here, so we'll still be at 0 volts. Okay, and so look, we still start at -2, we end at +2. Okay, we have a uniform change, okay, in the voltage because we've got a uniform electric field working against us. All right, so now what is the effect of that? Well, if I take and I do the same approach I did over here, so go delta V over D gives me the electric field. Okay, well now look at the gap. Okay, now the gap between these two plates is only 2 millimeters. See, because I'm putting a physical conductor in here. So let's see, so 2 millimeters, that'd be 0.002 meters. Okay, and if I do the math, okay, just by inserting that metal conductor, now all of a sudden this region here, all right, I've got an electric field not of 800 like I had before, but 1,000. Okay, now of course, we still have to satisfy conservation of energy. The trade-off is that inside here we get nothing at all. So for including this conductive plate, okay, what does that do? It increases the electric field, but only for the part, okay, in between the plates. See, so like when we get to that middle plate, okay, the voltage or the electric field is going to drop down to 0. Okay, but then when it leaves again, it's going to spike back up to a higher value. See, so we get this. What is that? So it's continuous, but it's like a piece function. Okay. What about the voltage? Okay, well, we're going to hit 0 volts, but we're going to hit it sooner, and we're going to have a place on our voltage graph where the voltage doesn't change. All right, the electric field is stronger than it was before, so the slope is going to be larger. So we get this. Okay, so we come up to 0 volts. We have a period where there's no voltage, so that'd be like when we're moving across the plates. Okay, and then our voltage rises up to that same value, to that same positive 2 volts. It just does it over a shorter distance. So the slope is going to have to be bigger. Okay, so we get a different shape here. All right, now why I show this to you, because well, what's really happening is by inserting this conductor, all right, the electric field is increasing versus if I insert the dielectric, it's decreasing. Okay, and if we use a little bit of imagination, all right, we could keep putting in more of these things. Okay, and filling in the space, the electric field gets bigger, gets bigger, gets bigger, gets bigger. But at some point, all right, we don't have a capacitor anymore. Okay, we just have a conductive path that we call like a wire. Okay, and that's more current electricity stuff. So that's a topic, okay, for another day in another video. This one's already long enough. So this is Mr. Zizek saying thank you for watching, and I will see you next time.